Good day. In this lecture, we will be discussing about the BLAST or the Basic Local Alignment Search Tool. So basically, what is BLAST? So Stephen Atsul of 1990 stated that the central idea of the BLAST algorithm is to confine attention to segment pairs that contain a word pair of length W with a score of at least T. So basically, it's a tool used for sequence alignment. So you have here segment pairs of a certain length T. So it's a local alignment tool. So you have limited word pair lengths and they assign score there of T. But it takes much more than that. And in this lecture, we will be discussing more about what BLAST is. So here are the learning objectives. So we will perform or learn to perform BLAST searches at the NCBI website and understand what are those BLAST search parameters that we have. And we can also have what exactly is BLAST doing while we are waiting for our results. So how does it actually do? How does it run in the background? And basically the general flow of the algorithm. And for the results, we would learn on how to interpret the results. So what's the mathematical relationship between the expect value that you will see there and the scores and even the P? And of course, last but not the least, what are the strategies of a normal or a blast search? What can we do with blast? So as a background, first, what is BLAST? So BLAST is basically the acronym for Basic Local Alignment Search Tool. So it's the main NCBI tool for comparing a protein or DNA sequence to other sequences in the various databases. So your BLAST search, it allows the user to select one sequence, which is your query, and perform pairwise sequence alignments between your query and your entire and a certain target database. So here are the options for a normal web blast. So these are the most common ones. So you have the four common blast search, the nucleotide blast, which search nucleotide to nucleotide alignment. So the blast X, which have your translated nucleotide. So meaning your input is a nucleotide, it translates it to a protein, and it aligns the translated nucleotide, which is the protein translated into a protein into other protein database. So T-BLAST N is the other way around. So you have a protein and you would align it to nucleotides. So it will translate your nucleotide and align it to nucleotide database. And then for the protein blast, it's protein to protein alignment. So other specialized searches available in the website, you have the Smart Blast. For these are more on specialized applications for Blast. So actually all of these. So for the Smart Blast, it's to find proteins of highly similar to your query. So it can be a very the change could be for single one amino acid differences, something like that. And then the primer blast, it allows you to design specific primers for a certain PCR template. So it allows you to actually design your PCR. It helps in the design of your primers for PCR. In the global align, you can compare two sequences across an entire span. So this is for global alignment. It runs the Needleman Wunsch. So usually, if you want to compare genes or homologous genes, decently related or rather proteins with known homologies. So you can do this one. So this is global alignment rather than a local alignment, which BLAST by default does. So CD search, it's for conserved domains, finding specific conserved domains in the regions. So it can be for very distantly related proteins or even proteins that are not actually related to one another but are classified as, let's say, a same classification that shares, say, some conserved domain, some parts of their structure have, for example, similar zipper nucleotides, sorry, uh, the zinc, what do you call this one? You have certain domains in the structures that is reflected on your uh, sequences. So they find stretches of that domains that are conserved between the proteins. You also have immunoglobulins, the IG blast, for immunoglobulins and T cell receptor sequences. Obviously, this is for usually for when you want to design vaccines. And then you have VEX screen, for vector contamination. So you search sequence for certain vectors contamination. So when we say a vector contamination, it could be um, contamination experimental data, or it could be a chromosome that is contaminated with a virus. So because a virus in their lysogenic cycle, they incorporate their DNA into the genome of the host. So you can find possible contamination of viral vectors in the gene in a certain stretch of DNA. Then CDART, so find sequences with similar conserved domain architecture. So it's similar to the CD search. So you have here conserved domains versus conserve the architecture for similar domain architectures. And then you have multiple alignments. So obviously this is for not more than two alignments. So you have here domain and protein constraints for your alignment tools. You also have MolBlast. So it's established taxonomy for uncultured or environmental sequences. You have sets of genes or genomes uh, that are sequenced from actual environmental sources. You don't know if it's identified or not, if it's a new strain or not. So you can do MolBlast on that. So why do we use mole blast? So there are actually a variety of reasons to do blast. Sequence alignment is actually the most basic, one of the most basic skills. I say skill, but well, it is also a skill because interpreting it takes a while getting used to. It's a tool and a skill at the same time. So aligning sequences is one of the most basic things you do in bioinformatics. So most of the time when you look at studies involving bioinformatics, it almost always have alignment search. And when we do alignment search, the most common one is of course the blast search. So the historically we use it to determine orthologs and paralogs for protein or nucleic acid sequence, but in a more of a functional view, we are looking at how it applies in medicine or in practical research in environmental research. So we can use the blast search also to determine what proteins or genes are present in a particular organism. So if you have a genome of an organism, you can have from their ORFs, these open reading frames, at least have an idea what genes, what possible proteins can be obtained from those ORFs or identified ORFs in the genome. So we can also use, they are also used to determine the identity of a DNA protein or a sequence. So you have an unknown sequence of protein. You don't know if it's already discovered or not. You have no idea what that protein or DNA is. You do a blast search if you have hits that meaning that protein was already discovered before and was in the database. You can then identify your protein. If it's not in the database, it could be a novel protein, but don't jump to conclusions just yet. So there are other strategies for that. But anyway, you can also do blast search for discover new genes. So usually, since the genomes are already most genomes are already sequenced. So, but as we said, we know the sequences, but we don't really understand the whole thing. We have the record, but we don't know how to read all of them yet. So we can use the blast search to discover new genes from the very, very old genome sequences. For example, the human genome that was fully sequenced way back at, I believe it's 2003. And still we are still discovering new genes for that. Even for the bacterial genomes, it's very fast. There are many genomes now for bacteria, especially for the microorganisms that are used in the industry. You have industrial applications or even no as model organisms. These genomes are already sequenced, but we can still discover new genes, and that would warrant journal publications in itself. So determining what variants have been described for a particular gene or protein. So these variants can be a cause for the disease, or it can have loss or gain of function mutations. So we can know what are the variants of a certain gene or a particular protein, and what could be its functional significance or its phenotypic significance. We can also use BLAST for investigating express sequence tags so that this may exhibit alternative splicing. So a single ORF can have multiple proteins, a single stretch of a gene, or a single stretch of a nucleotide in the DNA that has an ORF. It can have multiple splicing, because remember, in the central dogma, you have post-transcriptional modification. And among the post-transcriptional modification, you have the alternative splicings. And so these alternative splicing events can be seen with the express sequence tags. The ideal tool for these alternative splicing events is for RNA-seq studies. So you sequence the mRNAs, the mature mRNAs which have already been spliced, and then you can relate it through sequence alignment. You can relate it to the source nucleotide, the source DNA stretch, and then you'll be able to then see if there are exons, introns, or are there any alternative splicing events. And also, last in the data, but not the least, and not definitely not the only last one, is to explore amino acid residues that are important in the function and or structure of your protein. So these are usually seen in highly conserved regions of proteins, especially in homologous proteins. You have very highly conserved regions, and that means that has a very significant functional or structural significance. When we say functional, so it can be the catalytic site of the enzymes. When we say structural, it can form it has a great contribution to the stability of the tertiary or quaternary structure of your protein. So you have here your components. When you go to the NCBI blast, so these are screenshots of the blast. This is for standard nucleotide blast. So as you can see, it's a blast N. So here are the four components, four basic components when you perform any web blast search. So first, you have the sequence of the most how should I say, the most glaring or obvious one is the query sequences. So here you would enter your query. So you can either enter it or upload it as a file. You can put job title. So if it's if you use a session number and you don't want the whole sequence to be analyzed, you can just specify the sub range for the query. So, and then although this is some of you might not be able to anyway, look at the tabs. So not as prominent as the query, but the tabs here will tell us this particular blast program you want to use. So you have the blast N, blast T, blast X, T blast N, and T blast X. So you also have a database search. So this is the database against which you will align your query. So this will be the database of the targets you have. So you have your you can specify what specific database it's. Usually by default we use the standard databases. And the algorithm parameters. So you can also add here additional algorithm parameters for you to actually see, or you can have additional parameters you want to modify. So this is usually hidden, but you can expand this tab, the last tab at the bottom, for you to modify, to add additional modifications. So how do you perform a basic blast search? So first, look at the program. So when you, the landing page for the blast is this one. So when you go to the blast, you will see first this page. So this allows you to choose what program you have. So these are the actually this is now the five basic blast programs and how it does or what it does. So for the blast P, this is straightforward protein query versus a protein database. So you just have a single number of database searches. So your query is you have a single query, you search it to a database of proteins. So for the blast and the same as protein, the difference is that you are using nucleic acids and nucleic acids in the form of a DNA. So this is, take note, you have T instead of U in your sequences. So make sure when you enter your nucleotide sequence, you have T's instead of U's because this is a DNA to DNA sequence. Now, how about BLASTX? So BLASTX is translated DNA. So you have here DNA translations. So why do we have six protein sequences? So remember, you have multiple codons in your protein. So you have your DNA sequences, it translates into six protein using six possible reading frames. So you have a nucleic acids. And of course, remember the reading frames, the open reading frame starts from methionine, the AUG start codon, and ends with any of the three stop codons. Now, in your DNA search, you can find, because remember how the translation works in molecular biology. Oh, by the way, in bioinformatics, you must be in order to properly understand most bioinformatics uh, concepts, you must have a grasp of your molecular biology. Now, remember in the open reading frames in translations, searching for the start codon, you scan the whole DNA first. The DNA does not always necessarily start with AUG. It's not as convenient as that. So you can have AUG appearing near the start, at the middle, or even near the end. So it scans for six possible open reading frames. And these open reading frames are translated into protein. So you have multiple proteins, actually six. You have six possible proteins that they do blast P on the six proteins. So it's blast X is just like translating your DNA into six possible protein products, and then each protein products they do blast P on each of the protein products. So you have protein to protein alignment again, but you have six queries basically. The For the T-blast N, it's you have your DNA sequence. So you have a protein. You start with a protein, and then your protein used to translate every DNA sequence in a database into six potential DNA proteins, and then compare your protein query against each of those translated proteins. So basically, again, it's somewhat the reverse of your blast X, but in here, your DNA sequence in your databases are translated. So you have PBLAST, basically, protein to protein alignment, but the instead of the query being translated to the protein, it's actually the DNA from the target that are being translated into at least six proteins. And it's actually more time consuming because if your database contains a large amount of DNA, each of them would be translated to six. So your target database would be six times larger. And so you would have a larger sequence to actually align. And then you have the blast X, which is much, much longer and more laborious because it's the combination of the blast X and the T blast N. So basically, you have here DNA, you input a DNA, the output is also DNA sequences, but what they are comparing are the proteins that they are comparing. The alignment is being done protein versus protein. So as you notice here, the blast X, blast T blast N, and T blast X, they are being the alignment is protein versus protein. It just happens that you have to translate the DNAs, either if it's a target or if it's your query, or even if it's both. For T plus X is both. You have your query, which is a DNA, it translates into six possible protein sequences. And then it is aligned protein to protein against a database where this database is derived from a DNA database, and the each entry in the DNA target databases are translated to the protein. So you have 6 versus 6. So basically, you have a 36 protein database searches because you have the 6 protein queries from your query, and then your database, you have a data six basically your DNA database is times 6 because each entry in the database, each DNA in the database is being translated to 6 possible proteins, and the alignment is done protein to protein. So that's your these are the blast searches that you have. But most of the time we would be doing blast P and the blast N. So blast the translation, the translated protein to protein queries, um from my experience, I rarely use this translated query sequences. It's usually straightforward for me, blast P and blast N. But maybe in the future you might need to do translated searches in the database. Okay, so what are the key features of your, these are basically key features taken from their help page. So this is from 2019. So the last update from, this is from the help page of the blast. So you have the nucleotide blast. This is, the alignment is nucleotide to nucleotide. So it's the only nucleotide versus nucleotide alignment that you have. So you have also subgroups in that. You have megablast for sequence identification or intra-species comparison between different species. Discontiguous megablast for cross-species comparison. And blast N for queries, cross-species comparison. General one is the blast N, basically. And then you have the protein blast. This is protein versus protein. So you have blast P, the ubiquitous one, the general sequence identification similarity searches. You can have quick blast P. So this one is much faster with the k-mer matches to accelerate search speeds for very similar proteins, but as usually is the case with faster searches, if you want speed, you sacrifice something, and in this case, it's accuracy. And delta blast, protein similarity search with higher sensitivity than your blast P. So quick blast P is lower sensitivity, faster. Delta blast is higher sensitivity, but usually slower. Blast is iterative search for position-specific score matrices to identify distant relatives for protein families. So you want to sequence distantly related, or you have basically protein families. So you will see here proteins that do not really have a good alignment. So you have low identities there. So you have the blast. You have the fiblast on the other hand. You have protein alignments where you have anchors or constraints. For example, you want a certain you have a certain protein with a specific conserved domain or a region. You want to see that specific conserved domain accurately among all of the blast searches, and doesn't really matter for the rest of the protein, but you want a protein that have that same conserved domain. So you can do fiblast on that. And then you also have, for the blast X, this is translated nucleotide versus protein. So the alignment is protein to protein. So this is for the usual application is for identifying potential protein products included by nucleotide queries. So if you have also the blast N, protein to protein, again, as I said, told you before, this is for identifying database sequences encoding proteins similar to your query. And T-blast X, protein to protein again, for identifying nucleotide sequences similar to the query based on their coding potentials. So these are the key basic blast features that we have. Okay, so moving on. So once we have chosen the particular program that we want to blast, so basically to align, uh, that we want to apply or we want to use, we can now enter our query. So we can enter the accession number. So for example, here is your accession number. This is for a model sequence already curated because this is NP underscore. So you have accession number. This one is already curated and well considered a reference, standard reference for a model. So this is a retinol binding protein isoform. So you can even specify a specific version for this protein. But by default, if you don't specify a version, they usually use the latest version of this accession number. So unless you specify your version. So this is the FASTA format. So a FASTA format, you can copy paste it or you can save it as that FASTA. So this is the upload file. You can upload it as that. So as a that FASTA. So you have this search. So a FASTA format basically has a greater than sign and then followed by a line, a single line of this title. So anything goes here. You can edit this one to write whatever you want your sequence name, whatever you want to name your sequence. But this is only limited to a single line. So the next line must be your this is a protein query. So you have your protein sequence, your amino acid sequence, single letter format. So it can be as capitalized or not, depending on basically depending on you. Um, you can have capital letters, or if you download it in the database, actually it depends on the even in the NCBI database, you can see there are some entries where it's all caps, there are some entries where it's all small letters. But the issue here is it must have this sequence of amino acid. So this can stretch up to how many lines generally. So this is your FASTA format. So if you open a .fasta file, you will see this one. You open it in Notepad. Okay, so that's your FASTA. So you can, if you don't want to align all of them, say you just want to align from amino acid number 4 to amino acid number 10. So it will only just get this sequence, find the fourth amino acid, 1, 2, 3, 4. So from valine to the to the 10th one, 4, 5, 6, 7, 8, 9, 10. So valine to leucine. So it will only align this particular amino acid. So this is the query subrange. And you can enter uh, a title. So if you want to align two or more sequences, if you don't want it to align against a database, you just want to align it against your own, you have your own a target. For example, you have a one query and one target. You just want to compare these two. You can just check this one and it will give you another entry form where you can enter your FASTA or accession number of the target. Okay, and then this is for the database. So the step 3, so once you have input your query, you can now select your database. If you are not aligning it pairwise, you don't specify a specific target, it by default you are free to choose your database. So by default for the nucleotide, here is the default database, the NT. This is all GenBank plus MBOL plus DDBJ plus BDB. So it incorporates all of the major databases you have, except for the specialized one. So this is the specialized databases. And for the proteins, again, NR, this is for the default one. So these are non-redundant GenBank CDS translation, RefSec, PDB, SwissProt, so on and so forth. So you can also have specialized databases that you can choose depending on your application. So that is why it's important to know what you really want to do, what you really want to know about your sequence, because you might get lost or you might get overwhelmed because there are many possible options that you have. So, but anyway, by default, if you don't really know if you don't have specific ideas or specific database, you can just use the default database, the ND and the NR. Okay, so here is um, it's actually a drop down. So this is for the protein. Yeah, this is the protein. So protein nucleotide database. So you have this one, and then you have, this is for the uh, NR. This is for the protein database, this is for the nucleic acid database. Actually, if you look at these databases, you have specialized database, especially with beta coronavirus, with the outflow of information with this pandemic. We now have a specialized database for coronaviruses. So anyway, so these are the options for the database. So you can also have your exclude database. For example, you have this particular the default collection, but you don't want, for example, you want it intraspecies. So you have a certain human sequence coming from a human. You want to compare it to non-human. So you can exclude specific organisms. You don't want to include specific organisms in that. So you can enter this one here. So if you want to exclude specific models, reference models or uncultured. So anyway, these are all of the possible exclusion parameters. If you can limit your search, etc., etc. So you have actually, this question marks here allows you to have an idea what this for. It's usually for the help one. So the same goes for this one. So you don't want this for the protein sequences. So this is for the BLAST-P, this one for BLAST-N. So if you notice, you have, depending on the database, you have different options for them, specific for nucleotides, specific for the proteins. So exclude specific organisms. You don't want them to search for proteins coming from specific organism. You can exclude it. Or if you want to limit your search to only, for example, to only humans, you can put the humans here, but don't check here. It will exclude all human results. If you want to limit your search to all human results, you just put the humans, Homo sapiens here, and then that's it. You run the BLAST. So basically, these are the basics database parameters search. Okay, so other search parameters. So we have the quick blast, BLAST-P, blast, and so on. So if you want it fast, quick blast, but less sensitive, BLAST-P is the standard one. Blast is, you have PSSM, you have the blast. You specify alignments. So you have the delta blast for a more specific or a more sensitive one. But by general, you just use the BLAST-P. When in doubt, use BLAST-P. So anyway, this is the generic one. Recommended settings basically is the BLAST-P. Unless you have specific needs depending on your project or depending on your research. Okay, for the nucleotide blast, so additional parameters. You have max target sequences. So this is the display. The display page, the results page, you have a maximum of 100. If you want it to limit it, you want it more, you just change this one. So for short queries, this is default check. So it adjusts if you have short queries, because the calculation, the shorter you have, the more there are more, rather there is a more chance to have false positives in shorter sequences. So for the scoring, there must be some adjustments done for the search parameters. The default expect threshold is 0.06, and the word size because it's a local alignment, this is usually default 20, this default is 28. So the scoring parameters, so for the blast search, it doesn't really necessarily by default, it doesn't employ any of these the other models. It just employs the basic model. So if it's a match, this for nucleotide. If it's a match, you have a 1. Regardless whether it's a transversion or a transition change, it's still a match, it's a 1. If it's a mismatch, regardless of transition, transversion, it's still -2. So it uses the most basic scoring parameters. And the gap cost, for linear gap cost, you have a linear gap cost. So then low complexity. So filters and maxing. So you can filter out low complexity regions. And you have for masking, so for lookup table only. So anyway, this is additional filters and masking. So if your nucleotide has low complexity region, so there are regions that are these are actually quite more problematic in the future searches. You have these filters and masking. Okay, now for the protein blast. So the same, you have maximum target from the output, expect threshold, the word size, shorter one because this is a protein. So usually, generally, these are shorter because again, 3:1, you have codons for the nucleotides because nucleotides tend to be much longer than the actual proteins. Now, the scoring parameters, the default is blossom 62, but you can specify it to PAM, to other blossoms. So gap cost, So if you introduce gaps, the addition of a gaps, you add a gap. From no gaps to add a gap, you have a cost of 11. If you extend that gap, it's much smaller, the extension, so it's 1. So you have the compositional adjustments. And so also filters and masking. Okay, so I have here a blast sample search uh, in my NCBI. So let me stop sharing for a while and go to my search. So that you would know once you run your blast search, you would have an idea on what to expect. So let me share my screen again for my blast. Okay, so go to NCBI. Basically, in running the blast search, you have your blast. Okay, so this is the landing page for the blast website. So you have this blast. You have 5, actually, 5 blast, but you generally just have the 4 here. And then these are the additional specialized blast searches. So in here is the blast P search. So if you look at the protein blast, click on the protein blast, you would have your blast P, the query here. You can choose file, job title. If you want to align 2 or more sequences, if I check this one, so if you notice, I have another query here. So this is the target. You can either also choose a file here. So for the algorithm parameters, so take note that once I had checked this align, there is no database. It automatically jumps to the parameters, because that means it won't search for the database, but rather the target, it will search the alignment for the query. Your query will be aligned to this to what you input in the subject sequence. This will be your target. So whatever this is, you can have multiples here. So this is your specified one. So if you don't want, if you don't have a specified target, this is what happens. So you will have your database search. So you choose your specific database. So if I don't want to include my Homo sapiens one, so on and so forth. Okay, so these are the additional algorithm parameters. So here is your blast tool. So I have multiple ones here for comparison, but basically I have an account here. You can save your specific search. If you want to go back to that one, you can save your specific search. And where is that link? Okay, so ayaw niyo makita. Okay, view. Okay, here. You can view your search. So here is my search. And I can just run the blast. So this is NP. So I can just remove this one. Okay. So this is my NP and then run the blast. So this is the basic search. So because I don't want to lose this one, so I just click on. By default, it's not checked. So this is conditional compositional. So the scoring parameters is conditional compositional score matrix adjustment. So it automatically adjusts for short sequence and then it's running. So basically what is being saved here are the search parameters, but not the actual search results. So every time you go back, you would have a new search results. So that doesn't mean that you get exact same results every time, because this is a dynamic database. So any day, anytime, there might be some changes in the databases. And so you might not get the actual results always. So waiting for the submission time. So we're just waiting for this submission. So it's automatically updating. So basically, this is the general flow of how you do a search blast. So while waiting, so in the next part, Perhaps I'll just pause this video here while waiting for this one. And then the next part, we will continue on. Um, Basically, we will look at what are the changes between this compositional adjustment. What are these adjustment matrices mean? Because it affects how your blast scoring goes by. And then we will also see the results, how you can view your results. This is for the next part of this lecture. Here is the results. But anyway, I'll just stop here for a while and continue on in the next video.